In this machine learning video, we're going to learn about ensemble models. We previously looked at decision trees, support vector machines, and a few other machine learning models. Here, we will learn about this concept of combining or ensembling these models and using collective wisdom to see whether they improve the prediction or not. There's an interesting concept of wisdom of crowds that works on the same lines. We're going to look into that. Also, we will study about hard voting versus soft voting using a very simple and easy to relate example. We will see about bagging or what's bootstrap aggregating. How do we randomly take the samples out from the dataset using potential two methods, random patches or random subspaces, and what's the difference between those two? We will look at a simple Python example using alcohol dataset. What's regression trees? And what do we mean by extra trees or extremely randomized trees? What's AdaBoost or gradient boosting algorithm? These are pretty popular in making predictions and one of the most cliche algorithms that are used in machine learning. What do we mean by stochastic gradient boosting? And what do we mean by voting regressor and ensembles? All right, let's dive right in to the idea of wisdom of crowds. There's a very famous book called Wisdom of Crowds, and you can look up into Amazon for it. It begins with a fascinating concept with an experiment from a century ago. At this exhibition or a fair, there's an ox. This ox, they, they put in the center and ask everybody whether this ox with four legs, one, two eyes, nose, whether this ox, whether you could predict the weight of this ox or not. Everyone writes down their guesses and drops them into a box. Now, guess what? Nobody gets it right. Some people are way too below the actual weight, while others are way too high. Nobody gets it right. Here's the twist. When all the gases are averaged together, the results are astonishingly spot on and close to the ox's actual weight. That's the power of collective intelligence. When many independent opinions are combined and the results are found to be more accurate than single person's opinion. That's exactly what ensemble machine learning is all about. Think about it. When you're deciding to eat in a restaurant, you don't just trust on single review. You look at dozens of these reviews and then you make your mind about whether to go to this restaurant or not. When you invest in a stock, you read multiple analyst opinions before making your move. That's ensemble models for you. Each of these models are trained slightly differently. They work on their own methodologies, each making their own kind of mistakes. When aggregating them, you get a result that's way more accurate, more stable, and more robust. Even if individual models are weak, ensembles still can be more accurate than individual models. Idea is you build lots and lots of models. You build 500 of them, 1,000 of these models, 2,000 of these models, average down their probabilities, average down their predictions, and you get a prediction which is definitely more accurate than a single prediction or single model's prediction. How do you get sufficiently diverse model making different predictions? There are two ways, one and two. Different algorithms, that's easy. You can either use logistic regression, support vector machine, decision tree, and so on and so forth. That's one way to bring the diversity in machine learning predictions. The other way to bring the diversity in machine learning predictions is use same algorithm. Use just one called decision trees, for example, but train it on different samples of the single data set. Let's say you pick 50 rows here, 100 rows here, 500 rows here, and similarly you keep building 500 models. Sometimes you pick a section over here, sometimes you pick a section over there to make the predictions on your target variable. And this way you're building thousands and thousands of models. That's ensemble models for you. There's an interesting concept of voting classifier, hard voting or soft voting. Hard voting is same as what we do in the elections of the government. Each person gets one vote, and equal vote. For example, first algorithm, decision tree, second, support vector machine, third, logistic regression, and fourth, another algorithm. So all they all get a single vote. For example, three of them predicted the results to be one. You add them together, three in comparison to just one making a zero prediction. So majority says one. Final result is that the final result is one. That's what majority means in the hard voting concept. While if you use the soft voting idea, you use the probability idea. Whether how confident is this model about its prediction? It's 0.5, 50% confident. What you use to get these probabilities in Python is a function called predict proba function. When you use this with the model, it predicts with a associated probability. Probability associated with, let's say, decision tree is 0.5, support vector machine is 0.5, and logistic regression is also 0.5, while a fourth model gives its prediction of 0 using 0.6. Now, if you average down these three who predicted 1, you get 0.5467, while the other probability of the fourth guy is 0.6. Who is the one who is leading in terms of probabilities? Obviously, it's zero point 0.6. So 0.6 rules over 0.5467. So this way in soft voting, you get a prediction of 0. Same data set, same models, only difference is now we use probabilities. How confident is each model about their own prediction? We average down their probabilities, compared it with the opposing prediction probabilities, and we find out the opposing prediction probability are higher than three models suggesting the same thing. And this way, we make a prediction of 0. See, the difference is this guy predicted 1, this ensemble predicted 0. So each of them have their own use cases, and we're going to learn when to use which one. We're going to learn about an interesting concept of bagging. Bagging is short for bootstrap aggregating. Imagine you're running a big marketing survey. Instead of asking 1,000 people the same question, you ask different random groups of people a slightly different set of questions and then combine their answers to get an idea of all the 1,000 people. That's bagging, or short for bootstrap aggregating. We train the same model, example decision tree, only same predictor, not multiple, same predictor, same model on many random samples of the data, and we allow replacement. What do I mean by with replacement is, let's say this is big or full data set. I take a sample of 50% of the data. Here, I learn from this and give this 50% back to the full data set. So portions of it could be reused in another 50% sample. And this comes back and gets replaced in the full data set. And another random patch goes to the third model. And we keep doing the same thing, running hundreds of models on the same data set, realizing or learning different patterns. When we do not replace the data, it's called pasting. Final prediction is hard voting. Typically, by hard voting, what I mean is each model gets their own voting. Whatever the majority of these models would say, the final result will be based on that. But if you would like, you can also use soft voting, and you can tell the algorithm, I really want to use soft voting, even if the typical or default way is to do hard voting on the bagging algorithms. There are two ways to sample the data. For example, I just talked about the big data set, and you're taking samples of this data set and making 500 different models out of it. How do you do that? There are two ways. One is random patches, the other is random subspaces. Random patches means sample from the training instance or sample from the training features, that is inputs. You can use this patch. What I mean by that, there are multiple columns in the data set. See, all these are columns. Sometimes we call them predictor or independent variables. And finally, we have a target variable. So all these are columns and these are rows. When I say random patches, you can literally use patches from the dataset. A patch 1, another patch could be 2, another patch could be from here, 3. So all these data patches are predicting their respective target variable. Different patterns are learned from this dataset and finally combined to give you an overall learning model that would be based on the ensemble idea. The other concept of sampling the data from the data set is called random subspaces. Here, the idea is you have the full data set, but you always use all the rows and you randomly select the features. When I say features, I literally mean the columns. You can have feature 1 or column 1, you can have feature 10 or column 10, and you randomly make a selection based on random columns to make the prediction of the target variable. This is the difference between random patches. Patch could be from just about a section from the data set, but subspaces literally has all the rows, but you are randomly selecting a set of columns from the data set. Here you could have 1, 3, and 5 for one model, 1 and 6 for the second model, 1 and 10 for the other model, 1, 8, and 9 for the fourth model, and so on and so forth. And this way you make your 500 models, 1,000 models. What's the problem with 500 models or 1,000 models? First, you will need a lot of computation power in your system. Second, you might be overfitting the model. If you learn too much just about everything from the data set, when the new data comes, you will expect the new data to exactly follow the patterns of the older data, which is something you don't want. And this concept we previously discussed is called overfitting. And you don't want to learn way too much from the model. And there are ways to reduce the overfitting. And we have discussed those for the most part in previous videos. One of the very popular models is called random forest, which is literally a forest of decision trees. Nothing new I'm introducing here. We looked at decision tree machine learning algorithm before. This is simply a forest of decision trees. Each tree looking at different random subsets or subspaces of the data and trying to make their own predictions. The forest votes and the majority wins. In business terms, that's really like asking a panel of experts. They all look at the market from slightly different angles and you get a balanced prediction than relying on just one expert. That's what random forest, a forest of decision trees for you. Random forest is practically bagging with decision trees. We looked at what bagging is. Bagging is bootstrap aggregating. By that I mean aggregating the responses of individual models and aggregating them. So bagging of decision tree, making a big bag of decision trees with replacement, and that's something we call as random forest algorithm. There are two kinds of random forest algorithm, obviously. One is for classification problems, other is for regression problems. Very important to hyperparameters. Exactly same what we had in decision trees, maximum depth, and everything that pertains to the decision tree, and everything that pertains to a regular ensemble algorithm. That's number of estimators or how many decision tree you really want. Do you want 500 of these decision trees, just 100 of them, just 20 of them? That's how you define the different hyperparameters. One, that's everything what decision tree have and everything what typical ensemble model have. There is another concept of extra trees. You know, randomness makes you stronger. So they introduce a concept of extremely randomized trees to add more to the randomness, to make the whole mix even more chaotic than a regular random forest. These take the idea even further. Instead of carefully finding out the best split in the data, like we do in decision trees, this extra tree or extremely randomized tree splits the data at random locations. Let me remind you the concept of decision trees. So, for example, this was your data set. Oops, it looks so bad. Let me erase this. So if this was your data set, all these different points on the data set, and circle represents the person really had alcohol, while the dots or lines represent person people did not have alcohol. So a typical decision tree model draws a very optimized line based on the majority data set and separates out these circles from the dots with few impurities. So these two would be impurities in our case. But what extra trees or extremely randomized trees would do, it wouldn't think where to draw this line. It would just draw a random line here and try to find out what's the residual or what the remaining uh, impurities are. And it keeps drawing these lines, some horizontal, some vertical, without thinking. A typical decision tree would think, extra trees or extremely randomized trees would just draw random lines, and it would rely how it will get the good prediction. It will rely on the idea of ensemble models. It will rely on the wisdom of crowds, that eventually if I make 2000 predictions using some random division in the data set, I will get it right eventually. And that's what extra trees is for you. Why do we need this algorithm? What's the use case of doing all this random work and running 2000 different models? Well, it's less computationally intensive than a random forest algorithm. That's the biggest advantage of doing this. And it's way faster because it's not thinking, it's not using its computation capacity to find out where the majority data set is, or how do I separate majority from minority to make the predictions. To understand what decision tree really does, if you don't remember, go back to my previous videos. All right, let's go on to the next concept of boosting. What do we mean by boosting? Now, let's flip the story. Imagine you are a coaching sales team. You're coaching a sales team. Each person tries to pitch your product. Some do great, while others fail. So, for the next session, you focus on the people who struggle only. People who succeeded, great. People who failed, I want to work on those people only. Over time, the whole team gets better because you really focus on the weaker ones. They say you are as good as your weakest link. And when you work on your weakest link, the overall model, overall prediction becomes even better. That's the idea of boosting. It refers to converting weak learners into strong ones using this ensemble concept. How do we do that? We train the predictors sequentially. Previous approach of training the models are independent of each other. Boosting involves one model that is tweaked after each iteration. So we keep doing all these iteration, keep training the weaker ones. We keep improving the weaker ones, and finally get a prediction that is very good. There are two types of boosting. One is adaptive boosting, other is gradient boosting. I'm going to describe this concept in a little more detail. But let's look at what's AdaBoost or adaptive boosting. Obviously, there are two kinds, classification and regression. It fits the models in a sequential manner, and you can stop the fitting when desired number of models are reached. There's an interesting concept of instance weights and model weights that gets involved in this iterative training the weak guy process or training the weakest link process. Here is how it works. This is your data set, all these blue dots. You learn, do the machine learning. What comes out is a regression line. It learned from the data pretty nicely. But what it did not do good, it missed out this guy and maybe a few more guys like that one. Now the algorithm goes back to see which one did I miss. Oh, this guy is the one I missed. What it does now is it boosts the weight of the underfitted instances. This guy is the underfit instance UI. It boosts the weight of this guy, and this time the algorithm makes sure it works on the weakest link. It starts here, make sure to cross this guy, but in this process, it misses the stronger guys. Just like we discussed, you are as good as your weakest link. So this time it learned from make sure that I learned the weakest link. But now it missed the other important guys in the whole algorithm. So these guys are missed. Now it's going to learn the missed ones or the underfitted instance. So the previous guys are the new UIs, which were stronger, but still now they were missed because it was trying to make sure to pass or learn from the underfitted ones. Now the new ones are the previous fitted instances. Now it boosts the weight of these instances, learns from these guys, and this is my new model. So I got model 1, model 2, model 3, and I keep doing the same thing. And each time I keep making some or the other mistake because I'm trying to focus on the weaker links while forgetting the stronger ones. And each time my weak and strong keeps mixing and matching, and I keep generating hundreds of models. What's happening here? I continue to generate some strong, some weak, some average models in this process of learning from the weak or improving the learnings from the weakest link. That's called adaptive boosting, or in short, we could call it as ADA boosting. What's getting boosted here is the weight of the underfitted instances. You keep doing that, keep generating thousands of models. We combine all of them using hard voting or soft voting and make a final prediction based on 1,000 models. Your prediction is going to be pretty accurate. That's all adaptive boosting for you. So let's dive a little bit into what's theoretical difference between instance weight and model weight. Here we looked at the weight of the underfitted instance. That's exactly what instance weight is. Each weight or each instance has a weight of 1 over n. After training 1, the weight of underfitted instances, like this solid blue data point, is boosted. These weights determine how to fit the next model, and that's the concept of instance weights. When we talk about model weights, each predictor's weight is computed based on its accuracy. Those which are more accurate get higher weights. Those that make random predictions have a weight of 0. Those that make the model worse than random predictions have negative weights. So the model decides which feature or which column is making a good prediction. So a random patch may be assigned a lower weight because that typically is making a poor prediction. So it helps the model improve its accuracy by 2 methods, instance weights and model weights. So AdaBoost uses both these concepts to make the prediction, and that's how it gets its improved accuracy over a regular decision tree. Now, let's look at specifically AdaBoost classifier. Each model makes a prediction. Model weight is used to calculate weighted predictions. Majority vote is used for the final prediction. We looked at what majority voting is, how weights are calculated to calculate the weighted predictions, and finally, AdaBoost or adaptive boosting classifier makes its calls or its predictions. There's another concept or another algorithm called gradient boosting. It only uses decision tree. It does not reweight the data but instead it fits new models to the residual errors. I'll repeat, it does not reweight the data, but it fits new models to the residual errors. We looked at new models fitting through the residual errors in the adaptive boosting as well, but the gap between what was predicted and what actually happened, that's what gradient boosting really works on. Think of gradient boosting like a team of analysts working for a forecast. The first analyst gives you a rough estimate. Second gives you what was missed in the rough estimate. Second analyst looks at what was missed and fine-tunes it. Third reviews the remaining errors and adjusts them. Each new model learns from the mistake of previous one, and together they form a highly accurate prediction. In business terms, it's like running a continuous improvement cycle in each iteration as it continues to get closer to the prediction. Here is the chart of residual predictions. So in the first step, green line is the prediction line and blue dots are the original data dots. So this is my data set. So in the first iteration, it fit a green line, but you see at this location, it has a lot of error. So ensemble prediction has a lot of error. What I mean by that, prediction equals to h1x1 and green line was h1x1. Now we look at the residuals. Residuals are what was missed. So this is my rough draft of a given analyst. Another analyst, what it does, it finds out what was missed and draws a line through it. All these data points, and so this it predicts on the residuals. It ran the algorithm of decision trees on the residuals. And now h1x1, which was this, plus h2x2 from residuals, h2x1 from residuals, improves the ensemble, and it continues this process, keeps improving the accuracy, and this is what gradient boosting is for you. It has its own improvement cycles, and it continues to improve the accuracy until a certain point, until you don't start overfitting the data. And that's how gradient boosting works. Some of the parameters you want to pay attention. If your learning rate is low, you need more estimators. By that, you need more trees. You can fix the number of estimators. If you got too many estimators, you might be overfitting the data. How do you decide whether it's too many or too less? It's based on the concepts we discussed earlier. If it's predicting too much in the training data set, for example, 100% accuracy, it's likely that it's overfitted because it's not going to be able to make 100% accurate prediction on the real world or test data set. So this is training and this is test. You want this one to hold as high as possible. If you're learning 100% here, and when you really test it, it's like 60%. So you're not doing a good job with training, and that's how you realize your number of estimators were way too much because I learned way too much here, and when it comes to the new data set, I didn't predict as nicely as I could. So what you could do to improve that, you can use the concept of early stopping to prevent overfitting. By default, the subsample is 1. By 1, I mean 100% of the data is read. But if you don't want the 100% of the data to be studied or looked at by gradient boosting regressor, you can reduce it to, let's say, 0.95 or let's say 0.85. So 85% of your data set would be looked at or studied, and 15% would be left from the subpatches or subsamples. When you leave the data set and you're randomly selecting the data, then you call this algorithm as stochastic gradient boosting algorithm. So it's stochastically or statistically deciding which features to select for my learning and which features to miss while not studying from 100% data to limit overfitting. So how do the regression ensemble models really work? It's just the average of individual regressors, and that makes the final prediction. For example, you start with three different models: decision tree, SGD classifier, SVM support vector machine, support vector regressor. So all three of these are regressors because you got a continuous variable to predict. Now, this guy, decision tree, predicted the value of your house to be, let's say, $200,000, while SGD, based on different parameters like locality and all those things, demographics, income, bunch of different variables could be there, a bunch of different columns or features could be there, and it predicted the value of your house to be $150,000. Similarly, support vector machine, based on some random uh, columns in the data set, predicted your house to be $160,000. Now we take a simple average, 200 plus 150 plus 160. Your predicted average based on three different machine learning algorithms comes out to be a $170,000. That's like a simple average. That's the voting regressor. So you are using regressors and you're doing a simple average. Simple average is add 200 plus 150 plus 160, divide them by 3. So that's simple voting, everybody getting their equal votes, and that's voting regressor algorithm. But if you use weighted average to thinking that that might improve my accuracy, you want to use like the weights. You think that decision tree is the one that makes a very poor prediction these days. I want to assign a weight of 0.3 only to decision trees. I think my reliance on support vector machine in the past have been really good for this kind of data set, though I'm taking some instance or some uh, feel from the decision tree, but I want to really rely on the SGD regression. Or so I assign it a weight of 0.6. Support vector machine, I think it has previously made really poor predictions. I assign it a weight of 0.1 only. This way, the algorithm takes into account the weights I assign. There's nobody else, no algorithm assigning these weights. I do a simple voting regressor using the weights, and I get a prediction of $166,000 for my house. Coming almost to the end of my presentation, what are the advantages of ensemble models? Ensemble models have ton of advantages. It uses the wisdom of crowd. It improves the accuracy of your models. The disadvantage is it slows down. It's a slow process because it's using a lot of randomness. If you if you use extra decision trees, you're not even learning, not even starting with the learned decision trees. You're starting with random decision trees. Advantage is it's fast and you can make thousands of models with limited computation power. But uh, the disadvantage is sometimes you get lower accuracy compared to like a random forest, which actually uses learned decision trees, which uses the majority rule to separate out the yes from no's or the different classifications within the target variable. So ensembles in general uses the wisdom of crowds, average them out to give you a good or better prediction than a single model. Summary is we studied voting classifiers, what's bagging, what's random forest, and what's boosting algorithms. And the same idea we studied for the regressors. Voting classifiers, it could be hard versus soft voting. Bagging is the idea that you want to put different sub patches from the data set and keep generating different algorithms, keep generating different predictions. You could improve on those predictions as you go on. One of the biggest example of bagging algorithm is the random forest, and you could boost the bagging algorithms by assigning the weights to the residuals, and that way you have boosting algorithms. So what you're boosting is the instant weight of the residuals or the missed or underfitted data points. Underfitted data points. When your weakest link is strong, you have bunch of models, some weak, some strong, and some average to make the predictions. and you average out, combine the feelings of all these models, and finally predict an accurate weight of the ox, just like the wisdom of crowds. And the same idea can be copied to the regressors, and you can have hard and soft voting there. You can have random forest regressors. All right, let's look at this ensemble example in Python. In this exercise, we are going to focus on underage drinking. This dataset contains the data of the high school student. Each row represents a single student. The column includes the characteristics of de-identified students. It's a binary classification task, and we are trying to predict whether a student drinks alcohol. That is 1, that represents yes, 0 represents no. That person or student does not drink alcohol. This is pretty important prediction to detect underage drinking problems and deploy intervention techniques. This dataset is called alcohol dataset. It's a CSV. The header of the CSV looks like this. The first 5 rows, I got age, travel time, study time, failures, free time, health, absence, and gender. And based on these parameters, I predict whether it's first I learn, then I predict whether the student would be potentially an alcohol drinker, or maybe or he or she would not be an alcohol drinker. We do the basic first steps to prepare the data pipeline. We split the data in test and train. We import sklearn or scikit-learn Python packages, and we separate the alcohol to make it a target variable. We run some basic feature engineering. We see how many columns, how many rows are there on each column, and we look at some basic feature engineering here. We look at travel bind when we bind them together, and we reduce the number of bins to 3. Some basic feature engineering stuff. Identify numeric, binary, and categorical columns. Finally, we come to our basic step to prepare the data pipeline. Use to get the numericals, categoricals, and binary separated using the transformers. And we have discussed all this in detail in our initial videos. We do the pre-processing of the data. We use that preprocessor with fit transform on the trained data set. Similarly, we use the preprocessor. This time we don't use the fit transform. We just use the transform and save it in the test data set. Then we do like a baseline comparison. What's the baseline prediction? How we do baseline is very simple, basic crude technique. Whatever is the most frequent classification in the target variable, we apply that to all of the targets. For example, if there are more ones than zeros, and we will predict we will predict ones for all of them, and this will give us a baseline accuracy that 52% of the time you will get it right. We tested it on the trained data set, then we tested it on the test data set. So about 52% is my accuracy just by using most frequent dummy classifier. Now we try to do the actual thing that we just studied. We looked at voting classifiers. We import scikit-learn tree that represents the decision tree, import the decision tree classifier, SGD classifier, logistic regression, voting classifier. So all these 4 different algorithms using the scikit-learn pretty popular package in Python for machine learning. We do the voting classification. DT represents the decision tree, LR logistic regressor, SGD classifier. Sorry, logistic classification, and we do the hard voting. So each of them gets one single vote, equal vote, and none of their votes in this model is higher or lower. Everybody gets their equal vote. We maxed our iterations number at 1000, and now we run the model. So voting classification, we predict the trained data set, we get 83% accuracy. We run the same thing on the test data set, which is pretty close to the train accuracy, and we'll accept it. We won't say it's overfitted at all because the test accuracy is close to train accuracy. And using the scikit-learn package, we do the confusion metrics. Now we do another variation in this ensemble. we do a bagging classifier. We use the SGD classifier with number of estimators. That means the number of trees or different decision trees that we're going to use. And maximum samples is 1,000. We run this bagging classifier. How this bagging classifier works, we already discussed, and we see if the accuracy improves. In trained data set, it's 82%. In test, it's 82%. That's tiny bit more than the testing data set. In We got 82 in the test for voting classifier, and we getting 82% again in the bagging classifier, which is about the same. No significant improvement. We do the random forest here, which we studied. Now, random forest gives me the accuracy of 84, which is higher than other bagging classifiers that we looked before. 84% in the trained data set. What it does is it uses 500 estimators. Maximum depth of the decision trees is 10, and that's what I use. 84% in train, but 81.2% in the test. This is lower than the bagging classifier and the voting classifier. Now we see a little bit tiny bit lower reduction in the accuracy. Now we use the AdaBoost or adaptive boosting classifier. How it works is, again, number of estimators is limited to 500, depth of trees is limited to 5, learning rate is also limited to 0.1 so that we don't overfit the model. Now my accuracy in the train is 88%, but in the test, the actual environment, it's 81%, 81.8, which is pretty close to the random forest accuracy. 81.2 was my random forest accuracy, and AdaBoost gave me 81.8, tiny bit more. Now gradient boosting classifier, which is I incrementally improve my models on a gradient by fitting the data on the residuals. The accuracy I get is 81.9 in the train and 81.1 in the test. That brings me at the end of this video. I hope you are able to follow all the Python, and I wish you a good rest of your day. And if you got any job or potential job openings, please feel free to reach out to me.